Hello everyone, and welcome back to Draft and Dialogue. Today, we're pulling into the express lane of technical drafting as we explore the efficient world of one-view drawings. One-view drawings. Think of these as the express lane of technical drafting. You use a one-view drawing when you can fully describe a part with just a single view, plus some smart notes. These are perfect for two main types of simple geometries. First, for flat parts with a constant thickness. Imagine a simple metal bracket or a gasket. Instead of drawing a front and a side view, you just draw the one view that shows its unique shape. Then, you simply add a note like thickness 6 mm right next to it. Boom. Done. The note tells the machinist everything they need to know about that missing dimension. The second classic case is for simple cylindrical parts. Think of a straight rod or a simple spacer. Here, you draw a single view that shows the length, but you represent the axis with a center line. Then, you dimension the diameter using the diameter symbol. That one symbol and dimension instantly communicate that the entire part is round, eliminating the need for a second view. Now, let's build on that idea and get a little more complex. You might be thinking, okay, a solid rod is easy, but what if my cylindrical part has a feature on it, like a hole? Great question. Let's take a look at a round shape similar to our spacer, but this time, it has a hole in the center. Now, the depth of this hole can vary. It might be a through hole, meaning it goes all the way through the part, or it could be a blind hole that only goes part way down. But here's the powerful part. We can still represent this completely using only one view. We start with our main view, making sure we include that all-important center line. We dimension the overall diameter, let's say 60 diameter. Then, for the hole, we show its diameter with the diameter symbol, something like 40 diameter. Now, here's the critical part for clarity, how we show the hole's depth. For a blind hole, a hole that does not go all the way through the drawing convention is different, and it's crucial to get this right. We do not use the long hidden lines to show a bottom, because that would be confusing. Here's how we do it. We draw the hole down to its specific depth. At the bottom of the hole, we draw a horizontal hidden line that represents the flat bottom of the drilled hole. Then, we connect the sides of the hole down to this bottom with vertical hidden lines on each side. This creates a distinct, closed shape in the drawing that clearly shows the hole has a finite depth. We then combine this with a clear note, like 40 diameter and 40 deep. This visual, combined with the note, leaves zero room for misunderstanding. The machinist sees exactly how deep to go, and that the hole is not through. If it's a through hole, meaning it goes all the way through the part, we can represent this in the 2D view by using hidden lines. Those are the dash lines you see. They show the hidden edges of the hole on the far side, instantly communicating to the machinist that this feature passes completely through the material. It's this precise language of lines that makes technical drawing so powerful. The key is that the combination of the diameter symbol on the hole and the center line on the main view instantly tells anyone reading the drawing that this is a round, coaxial feature. They don't need to see a side view to understand the circular nature of the part or the hole. This one view, with its smart use of symbols and notes, conveys all the necessary information without any clutter. To view drawings. So we've seen how one-view drawings are perfect for those simple, flat, or cylindrical parts. But what happens when your part is just a little more complex? That's where two-view drawings come in. Now, pay close attention, because this is a key concept for drawing efficiently. On some objects, only two of the three standard views are needed to show the complete shape, without any ambiguity. You don't always need to draw the front, top, and side. Often, just the front view and one additional view, either the top or the right side view, are perfectly sufficient to tell the whole story. For example, look at this object here. See how it has a unique profile from the front. But from the top, it's just a simple rectangle. In that case, drawing a side view would be completely redundant. It would give us no new information. So, we save time and space by only creating the front and top views. This is the essence of a two-view drawing. The key is to always choose the two views that show the most characteristic contours and the most important dimensions. Alright, so you've decided your part needs the full three-view treatment. Now, how do you arrange those views on the page so it looks clean, professional, and easy to read? It's all about balance. Think of your drawing space like a picture frame. You want your views to be centered and evenly spaced. First, the horizontal spacing. The distance from the left border to the side view should be the same as the distance from the right border to the top view. Let's call that distance equals C. This centers the entire layout left to right. Next, the vertical spacing. The distance from the top border down to the front view should be equal to the distance from the bottom border up to the top view. So, E equals F. This centers everything top to bottom. Finally, and this is crucial for a clean look, the gap between the views themselves should also be equal. The space between the front and top views should be equal. Let's call that S1 equals S2. By following this AC, EF, and S1 S2 rule, you guarantee a perfectly balanced and professional-looking drawing every single time. So we have our two views, the front and the top. The big question is, can we actually build a 3D model from just these two? The answer is, sometimes yes, and sometimes no. Let's figure out which one this is. The key is to see if these two views give us all three primary dimensions. Think in terms of X, Y, and Z. From our front view, we can directly measure two dimensions. We can see the height, which is our Z-axis, and it's 5 units. We can also see the width, which is our X-axis, and it's 6 units. Now, the missing piece is the depth. Where do we get that? We look at our top view, and there it is. The top view shows us that the depth, our Y-axis, is 5 units. So let's check our list. X width, 6 units from front view. Y depth, 5 units from top view. Z height, 5 units from front view. We have a value for all three axes. That means this object is fully defined. There are no hidden surprises in the third dimension that we don't know about. So yes, from these two views, we have all the information we need to confidently create an accurate 3D isometric drawing. Alright, now that we know we have all the dimensions, let's start building this 3D model in our minds, and we're going to start from the top view. Looking down at the top view, I can see we have two distinct L-shaped features. Now, the top view by itself only gives us a flat. 2D blueprint, it gives us the X and Y coordinates, the plan. To make these shapes three-dimensional, we absolutely must refer back to our front view to get that crucial third dimension, the Z-axis, which is the height. So, let's break it down step by step. First, we'll tackle the larger L shape. From the top view, we can see its footprint, its length and width in the X and Y directions. Now, we look at the front view to find its height. We can see that this main block has a full height of 5 units. So, we extrude that large L-shaped footprint downwards to a height of 5 units, creating the primary solid block of our object. Next, let's look at that smaller, interior L shape on the top view. This represents a step or a recess. We can see its unique shape and dimensions in the X and Y plane from above. But how deep is this step? We find that answer in the front view. Looking carefully, we can see that this recess has a height of 2.5 units. So, to create it in 3D, we would take that smaller L-shaped area and cut it down, or extrude it downwards, by 2.5 units from the top surface of the main block. And just like that, by combining the shape information from the top view with the height information from the front view, we've successfully translated our 2D drawings into a complete 3D object. We've proven that these two views work together perfectly to define every part of the geometry. So, we've seen how a one-view drawing is the express lane, and a two-view is the smart, efficient route. Mastering when and how to use them is a true hallmark of a skilled drafter. Thanks for watching Draft and Dialogue. Until next time, keep drawing and keep dialoguing.